Welcome to all our viewers. This is the second video of the chapter 14 of the crystal clear electronics. Let's continue with some simple but handy optoelectronic devices. Before discussing optocouplers and optical encoders in detail, it is worth clarifying what the term optoelectronics actually means. Optoelectronics is a branch of electronics that deals with light emitting and sensing components. To put it simply, it includes anything that relates to light, such as the photoresistor discussed in the previous video. Let's take a closer look at some devices.
Thank you, Bence, for the introduction. As the name suggests, an optocoupler, also known as optoisolator, transmits a signal between its two pairs of terminals through light. As you can see in the figure, an optocoupler can be divided into two main parts. One is the light-emitting side, such as an LED. The other is the light-sensitive side, usually a phototransistor. Its operation is very simple. When a few milliamps of current flows through the LED, it emits light inside the component, and as the phototransistor picks up this light, it opens and acts as a short circuit. Depending on the application, you can choose from a number of versions. Often, a single case contains multiple optocouplers. The light-sensitive side has several different designs: photodiode, bipolar transistor, triac, or FET. When using an optocoupler, you have to decide which output type to use and design the circuit accordingly. You cannot replace an optocoupler with a different one if their output types are different, for example swapping out a FET type to a triac type without redesigning the circuit. It's worth mentioning some of the technical parameters of these devices. Usually, optocouplers are used to bridge a potential gap between two parts of a circuit, or to make the signal immune to interference by separating the signal grounds and avoiding a ground loop. Their most important parameters are isolation voltage, the maximum voltage that the device can tolerate between the input and output side for a long time. You can use the optocoupler for signal transmission up to this voltage. Anything higher may cause damage. Forward current of the LED, the recommended current to drive the LED with to ensure that the output will be operated safely. If you use a smaller current, the output switch may not close completely. Generally, optocouplers are used for digital signals, i.e. the output is either open or closed. They are not very good for linear applications. This means that it usually makes sense to use recommended forward current. Switching time. Because the switching device on the output side of the phototransistor is activated by a low-intensity light source, it takes time for it to fully close. When the LED is not active, the output state has to revert to an open state, which again takes time. Turn on and turn off times may be drastically different, so it is worth it to check both in the datasheet. Because the minimum time it takes for the device to switch is limited, the device has a maximum usable frequency limit. Transmitting a signal with a higher frequency than that is not guaranteed to work. Current transfer ratio. It is also an essential property of these components. The CTR shows the maximum ratio between the output current and the input current. If you use a higher current on the output side, the output switch may not be able to close properly and the device may be damaged. This value is usually between 10 to 400%. The next component is the optical gate sensor. This device works the same way as the optoisolator. It has a light-emitting part and a light-sensitive part. However, its construction and area of application is different. Instead of the two parts being enclosed in a case, they are separated into two parts with a gap between them. The light traverses through this gap where an external mechanical object can interrupt it. They are most commonly used to detect position, for example the end position of some moving object. If you attach a narrow strip of solid material to the object in such a way that when the object is in the end position, the narrow strip slides into the gap on the device. This way, it blocks the light from reaching the phototransistor, which turns off, indicating the position of the object to a circuit. In the figure below, the circuit controls an electric motor through an optical gate. If the gap of the optical gate is left open, the phototransistor turns on, which applies voltage to the gate of the N-channel MOSFET, turning on the motor. Otherwise, if an object fills the gap, for example a narrow strip of material placed on the axle of the motor, then the phototransistor turns off, which turns off the MOSFET, and the motor stops. If the strip is wide enough and the inertial rotation of the motor does not turn it further, then the motor always completes one full turn and stops with the strip in the gap of the optical gate.
If we take the previous example further and put several markings on the motor axle instead of a single one, we can use them to measure the amount or the speed of the rotation. To do this, we have to make a disc on which opaque and transparent lines are alternating. Usually, they paint black lines on a transparent material, for example glass or plastic. Then, mount the completed disc on the rotating axle and place the optical gate sensor in a way that the disc is rotating inside the gap of the sensor.
While rotating, the output of the optical gate opens and closes because the lines on the disc block and let through the light emitted by the LED alternatively. The opening and closing can be easily converted into voltage impulses with a resistor. The rotational speed of the disc, and in turn the motor, can be calculated from the time between two consecutive pulses or the number of pulses during a given time period and the number of lines on the disc. We can detect the amount of rotation using the disc as well. Suppose the disc has 200 transparent stripes, so in a full turn, 200 impulses will appear on the output of the optical gate. Since one complete turn means 360 degrees, one impulse means 360 degrees over 200, that is 1.8 degrees of angular rotation. We can use optical gates to sense linear motion as well. Instead of a disc, we need a tape with the same opaque and transparent alternating lines that we mount on the moving object, then place the optical gate so that the tape stays in the gap. This way, the number of impulses is proportional to the linear displacement of the object.
Szintén egy felhúzó ellenállás segítségével tudjuk a nyitott-zárt állapotokat impulzusokká alakítani.
This method is often used in inkjet printers and scanners to accurately position the head. The disc and tape shown here were once part of a printer. Let's look at an example again. Suppose we have a 200mm long tape, which contains 1,000 transparent stripes. In case of a 50mm linear displacement, we will get 250 impulses, which means that one impulse means 50 mm over 250, that is 0.2 mm movement.
The automatic hand dryers and taps also work in a similar principle to the optogate. One half of the gate could be on the device itself, but even if there were anywhere to put the other half of the gate, it would not be practical to run cables far from it, especially in a wet environment. For such problems, a separate device will help, called a refractive optocoupler.
The only difference is that the light-emitting diode and the phototransistor are not placed opposite each other, but side by side. Therefore, the output switch part will only conduct if there's a light-reflecting object in front of the reflective optocoupler. So, we can use this component to detect the presence of objects. The distance from which it can detect an object is also affected by the type of the optocoupler, the shape, color, and ambient lighting of the object to be detected. The reflective optocoupler has many applications because by examining the reflected light, we can draw many conclusions about the reflected medium or its changes. For example, this is how the previously mentioned automatic tap and hand dryer work, and also the various liquid detectors. If you consider it further, you can discover which other sensors work on the same principle as well. Yes, this is how heart rate sensors in smartwatches operate, because the reflected light changes depending on the oxygen content in the blood.
We will continue with a special diode, but only in the next part. Until then, we say goodbye. Bye!
Bye!